not going to introduce myself yet. I'll get to that in a minute. I like to start with math. So I put some decks of cards on the tables, and we're going to pass out a worksheet with directions on one side and a recording sheet on the other. The game you're going to play is called Close to 100, and this is in our program. It's a third grade game. Thanks. So the basic idea of this is you can take out the decks and shuffle them. They're new, so they'll need to be shuffled. They're all labeled, so if they get mixed up, they're labeled by letter. So you're going to play with a partner, so you only need one deck per pair. Thank you. So the idea of the game is going to be to deal 6 cards to each person. I'll wait. So you can do it however you want, but each person is going to get 6 cards, and you're going to use the 6 cards to create 2 two-digit numbers. So you'll only use 4 of the 6, and you want to create 2 two-digit numbers such that their sum is as close to 100 as possible. It doesn't matter if you go over or not. You want to create 2 two-digit numbers whose sum is as close to 100 as possible. And then add on the back on the recording sheet, there will be a spot for a sum and a spot for a score. The score is the difference between your sum and 100. So if your sum is 98, your score is 2. If your score is 102, your score is also 2, right? Because both of them are 2 away from 100. So this is a golf-like game. You're going for the lowest score possible. Go ahead.
I have to ask you a question. Is this a 2-digit number if I want to have 2? You can do 0 too? The first digit of my 2-digit number can be a 0? Are you sure?
See, you're teaching all the parents.
What's going on in this game? What do you think the point is?
To win.
Yes. Speaking of winning, how are the Giants doing?
Tomorrow.
They haven't started yet, so they're not losing.
Not yet.
They will win tonight, though.
They will. They will. Okay, sorry. So what's going on mathematically in this game? What are the kids supposed to get out of playing this? All right, so definitely some flexibility in working with numbers and thinking about the numbers, right? Addition. Definitely working on addition. Estimating. Some subtraction because the distance from 100, right, or difference from 100. There's a ton of place value going on in this game, right? So let me start with how many people on round 1 wound up with a sum that was not as good as your sum was in later rounds. You wound up with a sum like above 120 in round 1, right? Kids do it all the time. When you start, your scores are pretty lousy because you're not really thinking strategically yet about how to work with these numbers. And then as you play a couple of rounds, you start to develop a good strategy. Did anybody come up with a good strategy, or were trying to do something every time you looked at your cards? You were looking for something in particular?
Wild card.
That helps. That helps. And not a hand of 2s, right? 4 2s and a 1 and a 3 or something. 1 and a 0. So what were you looking for when you were trying to put your cards in the ones place? Cards that did what? Added to 10. So if I'm trying to add to 10 with the digits I put in the ones place, am I trying to add to 10 with the digits I put in the tens place? Because that would give us a sum of 110, right? That happens all of the time in the first several rounds. It takes the kids a couple of minutes to figure that out. That I'm trying to get as close to 9. I want a pair that equals 9 in the tens place. n equals 10 in the ones place because something happens there. And what we're really working on a lot is sums of 10. There's a whole standard in the Common Core about knowing facts that equal 10. These facts really are more important than most other facts because we have a base 10 number system, and this game is totally drilling it and how those work in our base 10 number system within addition, and a little subtraction too, right? So there's a lot of math going on here, practice with the math facts, with strategies, and a lot of place value stuff. And one of the reasons I picked this game is because it gets a lot of mileage. In second grade, they introduced close to 20. In third grade, we just played close to 100. In fourth grade, it goes up to close to 1,000. You get 8 cards, and you make 2 3-digit numbers. And then in fifth grade, they actually played close to 7,500 also, but close to 1 with decimals, to add up decimals to the hundredths to get a sum as close to 1 as possible. And it's all place value, right? So there's a ton of math going on here, and when the kids get done, they've actually practiced adding several 2-digit numbers, thinking strategically about how to position them, and worked on the place value, and they don't want to stop. If I gave them a worksheet with the same amount of math on it, they'd hate me. Any questions about close to 100 before I move on from this?
Do the kids eventually start to strategize about the 2 cards that they leave in their hand so that they know that they're going to be in a better position for the
next round? So the way it works in investigations is they just give the directions, and when I talk to the teachers, I'm very careful to ask them to model how to play the game without modeling strategies to be good at the game, right? Model the directions without modeling the math, so that it's left up to the kids to do some of the cognitive work. We don't want to steal the aha. Then they play the game, and at the end of the lesson, they share out. You know, Heather, I really noticed you were doing pretty well in rounds 4 and 5. Did you have a strategy you were doing? Do you mind sharing with us what you were doing? And several kids will share it. And they play the game more than once. So after it's introduced on that day, it will come up the next 5 days in Math Workshop as a station. And actually, kids will choose to play it during indoor recess sometimes also, which is cool that they're choosing to do math during recess time. So yeah, the strategies come up during the discussion at the end after they've played for a while, and then when it comes back up in Math Workshop, other students will often then start to try to apply that strategy.
Brian, can make a little point here too. As you did play this game, and picture yourself in a room with 20 kids. How is this different than the way you used to learn? Who's really doing the teaching in this lesson? It's not the teacher facilitating the instruction, it's the kids investigating and learning on their own and coming up with their own strategies. And it's amazing sometimes when you don't tell kids how to do something, you just have them do it. They may come up with a whole new way of doing something, and sometimes you really find out who your math geniuses are, because they'll come up with a really unique way of solving something. Meanwhile, they get to share it with the rest of the class, and it gives kids different opportunities. Geez, that answer we can get several different ways. So they're not limited in just being taught how to do it one way. They kind of come up with their own, and that's why you get this great buzz. There's a great math buzz in this room for the last 15 minutes. And that's what's exciting when you walk into classrooms and seeing kids participating in games like this.
And along those lines, a neat thing about teaching in this way also, and this game, is it self-differentiates. And by that, I mean every student, regardless of their level of ability in the room, could enter this game. But you can play the game at different levels, right? So the strategies you're applying and what you're doing with the game sort of differentiates. I couldn't give you a worksheet and have that self-differentiate. It's static. As soon as I hit file print, that worksheet can't change. But because you're dealing out the cards and there's a lot of different things you could consider, the game could be played on many different levels. And there are different versions of it. I can start to tweak the game. If I notice there's a group of kids who are ready to go a little bit farther, I can introduce a negative scoring variation, where if you get 98 as your sum, your score is -2. if you get 102 as your sum, your score is positive 2. And your goal at the end of 5 rounds is to get as close to 0 as possible, not the lowest sum possible. Now we're introducing negative numbers and adding and subtracting integers a little bit, but in a really concrete way. And it doesn't cause the kids to bat an eye. It's pretty easy for them to think about it because of the context. Anyway, off of close to 100, we've got a lot of other things to hit. So my name is Brian Cohen, and this is a game in our primary resource now, which is Investigations. We left Everyday Math this year to adopt a program called Investigations, K5, and this is one of the things we do in it. It is somewhat representative of the way we teach, though every day doesn't have a game in it. What's representative about the game is this idea of giving the students a math problem or task to work on and struggle with, allowing them work time, explore time, and not telling them how to do it. And then after we have a lot of different strategies and some shared experience, coming back together and talking about it, seeing different ways we entered and attacked the same problem. If there were strategies that were more efficient than others for getting us to an accurate answer, and then giving them problems afterwards to apply the strategies we discussed in our summary when they shared out their strategies, to apply those more efficient strategies to a new set of problems. So I want to be careful. This doesn't mean we're leaving math up to students to discover, like they're blindfolded and dropped into the endless dark forest to wander their way out, right? It's a very guided explore. We're setting up problems in a particular way, that there's something specific we want them to discover. And when they're working as teachers, one of the things we're doing, aside from differentiating, helping students who struggle and extending kids who are done more quickly, we don't teach investigations cover to cover. We skip lessons, we skip entire units, we insert other things. We need to make sure that investigations is meeting our students where we are, and we also need to make sure it matches the Common Core standards. That's what we're obligated to teach. And that means that we have to add some things and subtract some things, so we do that here. So I don't want to give you the false impression that this is our sole resource, or that we're picking it up and teaching it cover to cover as it was written by the authors. It is our primary resource, and we're doing a lot of curriculum work to ensure that it's aligning to the Common Core standards and meeting our needs as a district. Okay, so this is an actual student, legend has it, according to the article in the Arithmetic Teacher, which is one of the National Council of Teachers of Mathematics journals, that these were 2 actual students in the state of California back in the 90s. So 2 second grade girls solved the problem by showing this work. And my question is, what do we know about these 2 girls?
They know old-fashioned math.
Okay, they know old-fashioned math. All right, so when asked to explain why she did it that way, or her solution, Marcy explained, right is right, you always line the numbers up on the right, and then you add the numbers starting from the right. 7 and 8 is 15, so you write the 5 and carry the 1. 4 and 4 is 8, and 1 more is 9. So you write that down. There's nothing to add to the 3, so you just write that. Why did you line the numbers up that way? Because that's what my teacher told me to do. What now do we know about Marcy? Does that give us any additional information about Marcy?
She's a rule follower.
And you know what? I'll take that most days, especially on Fridays. She listens and she follows rules. Perfect. Anything else we know about Marcy?
Just that she adds the ones first, and I'm noticing when Jack comes home, he's doing the tens column first.
Okay,
I don't
so
know
you
if
don't
that's-
always have to do the ones first, but
Yes,
Marcy
it's
does.
throwing me off even.
Yeah. Okay.
She hasn't been taught to think about other ways of solving.
So this is maybe her only way to solve it. She hasn't been taught about that. Angela explains her solution by saying 7 and 8 is 15, so I had enough ones to make another 10. 4 and 4 is 8 tens, and one more 10 is 9 tens. There's nothing to add in the hundreds place, so it's just 3 hundreds. And when asked why she did it this way, Angela explains, I lined the numbers up like this because the 4s are both 10s, and the 7 and 8 are 1s, and it's easier when they're together. What do we know about Angela?
She understands math better.
She understands place value, right? If we look at the explanation from Marcy before, we didn't really have any evidence at all that she understood place value. She was certainly able to execute that procedure, write that algorithm. But we have no indication that she actually understands what's going on there or anything about place value. Anything else?
Is this true?
That, legend has it that these two girls actually
It sounds great.
existed.
It seems very, they just seem very mature.
The explanations are actually, and this is a typical explanation from an investigation student in second grade, because we spend a lot more time talking about place value and strategies based on place value. But in order to do that, we're delaying the introduction of the traditional algorithms. And the standards actually delay the introduction of the standard algorithm, the traditional algorithms, because they want us to spend more time on place value and strategies based on place value in the younger grades. So we still get to the way we all learned. What we're doing, though, is building a lot of understanding beforehand so that when we start bringing down a magic 0, because that's what you do, they can tell you why you do that. This is my favorite part. So in 4th grade, we introduce problems like this. In case you don't see where that's going. Which one's Marcy and which one's Angela? Right. Right is on the right. If you don't understand place value and you're just executing procedures, there's a danger to that, right? If you understand what's going on, I put the 10s together because they're both 10s, the 4 and the 4 because they're both 10s, and I put the 7 and 8 together because they're both 1s. When we start introducing numbers that you can't line up on the right anymore, that answer getting trick doesn't work anymore, and you actually need to understand stuff, Angela can still do it and Marcy can't.
Well, no, she would have had to add the 0.
Right.
Which
We
is
have
what
to
we
create another
Right.
rule to modify our previous rules to make this work, right?
That's what we used to do.
Yep. Yep. You just add a 0. And by the way, if you just added a 0, wouldn't it just stay 3.5? Like 3.5 plus 0 is 3.5, right? That's the understanding of math isn't there. We're really not adding a 0. So part of the reason I talk about things like this is because when we went to school, we learned a whole lot of tricks, like put the 0 there so they both have the same number of digits to the right of the decimal. Well, why are we doing that? Because it's easier. Well, why does that work? Is that legal? Can I put a 0 at the end of the number 4? Not unless I put a decimal there also. So why can I do it sometimes and not others? Why does that work? I don't know, just trust me. Right? That's not what I want from our students. And that's certainly not going to fill out our STEM careers going forward. So one of the things I'm trying to highlight is the place value understanding. Another one is if we go all the way back to the first slide of Marcy and Angela, eventually I do this every time. I'll just learn to put that at the end again. They showed their work, they got the right answer. Case closed, right? We're done. Awesome. And we get from parents as teachers all of the time, my son hates when he's asked to explain how he got the answer. Or, why do you have to show your work? I got the answer, isn't that enough? Right? And when we look at the answer here for Marcy and Angela, we would say, yep, done. They both got the answer, they showed their work, it's all correct, done. And then they both had to offer an explanation. And this is why we have kids explain their work, not just show it. And this is why it's sometimes more important to write an explanation than to just get the right answer. I'm not saying getting the right answer isn't important. Getting the right answer is definitely important. But they also need to explain. Otherwise, we never would have known that Marcy was missing a huge understanding that was really going to get in her way in 4th grade.
Could you show me, like, in a 3rd grade level, how would you show your work?
Yeah.
Could you just
What would
do
you
it,
say?
like, on the whiteboard? Like, can you write out, like, are you supposed to do 3, 0, 0,
There's a lot of
plus?
different ways you can show it. I don't have a dry erase marker. Tell you what, I'm going to show a bunch of 4th grade multiplication.
Go ahead, you can keep talking, I'll pull it up. You can write right on this. in a
Oh,
second.
okay, thanks. So I'll try to do my best to write on the Promethean.
Because I was one of those parents.
board.
I sent a letter to my son's teacher saying, he got the answer, show your work. I can't even show the work.
Thanks.
And I would be like, to James, I'd be like,
Yeah.
didn't your teacher, are you supposed to do pictures? Are you supposed to break it down? I was calling my friend Robin, like, what do you mean? I was like, I don't get it.
Right, and this is a big thing because we learned one way to do it. So when they ask us for help, we go to show them the one way we probably know, right? And that, but you know, it's not wrong, but it's not what they're learning in school yet.
Right.
So you have this guilty feeling for showing it to them, but you don't know what else to do. Gonna work? Rock on. Okay, so I just need to bring back for a second.
Yep, and you can just bring it back.
It's 347 plus 48. First of all, I usually write the problem horizontally rather than vertically because as soon as I put it vertically, you're sort of being funneled into thinking about how to operate on those numbers in a particular way, right? By putting it horizontally, certainly a student could stack them vertically, but you don't have to. Here's a 2nd grade way of doing it. I put the 10s together, I put the 1s together, and the 100s together, right? I don't like this strategy. I mean, informally, I'll call it falling mountains, right? I don't like this because if you try to do it with subtraction, you're going to walk into negative numbers. So this is sort of, again, informally, I'll call it a break it strategy. We decomposed both numbers by place value, 300 plus 40 plus 7, plus 40 plus 8. And then we recomposed by place value, put the 40 with the 40, put the 8 with the 7. A break it strategy always walks into negative numbers when you get to subtraction. I prefer, before we get to subtraction, what I'll call a keep it, break it strategy. So I don't have to do 300 plus 40 plus 7 plus 40 plus 80. Can't I just keep the 347 together and then add 40 and then add 8? Here's why it's not a good idea. plus 7 is 15, so I have a 15, but I can't write it all. So I need to decompose the 15, and I'm going to write the 5 in one spot and the 1 in another spot. And then I do 4 plus 4 is 8, which I don't write anywhere. Now I just keep this one in my head because I have a carried 1 that I need. So I add the 1 to it, and now I put this at the bottom. And without going any farther, so far, sometimes when I add numbers, I write them on the bottom. Sometimes when I add numbers, I take the sum and I break it, and I write part of it on the bottom and part of it on the top. Sometimes when I add numbers, I don't write it on the bottom or the top. I keep it in my head because I have to remember to do something else to it before I then write it on the bottom or break it and write part of it on the bottom and part of it on the top. We kind of rotely go through this procedure as if it makes sense and as if it's easy to understand. But when you think about all of that stuff that happens automatically for us, that's not easy to teach a student and why it works, if you care about why it works. When these algorithms were invented during the Industrial Revolution, we weren't trying to teach kids why they work. They're actually German in nature. The US algorithms aren't American, they're German. And in Germany, when they read numbers, they read them from right to left. So the algorithms operate from left to right. From right to left, sorry. Research tells us in the United States that more kids actually think about operating on numbers from left to right than from right to left. And that's probably because in the United States we read in English numbers from left to right. The first partial sum would give you the closest estimate of the answer, right? When I read this, I don't say 7 ones, 4 tens, 3 hundreds, I say 347, right? This algorithm in the US makes far less sense than it does in Germany. This algorithm makes far less sense in the US than it does in Germany. I'm not saying we shouldn't teach it. Certainly it's very efficient once you come to understand it. It's just that it takes a lot to get students to the point where they can understand it. If I do strategies like this in second grade and this in third grade, and then we resequence this so that I'm doing the 15, then the 80, then the 300, and then go from here to the traditional algorithm, it's actually a much easier transition to get kids to successfully do the traditional algorithm, and it makes sense. Because if I put this right next to a partial sums algorithm and color code the 15, the 80, and the 300, and color code over here, you can see you're actually doing the exact same steps in the exact same order, getting the exact same partial sums. And it's just a matter of, do I keep the number whole and write it on the bottom, or do I start to decompose it and put some of the numbers on top? That's the only difference between partial sums and the traditional algorithm, is whether you write the whole partial sum on the bottom or decompose it and write sum on the top. And it's a lot easier to teach the kids the traditional algorithm for understanding if you've done partial sums first.
You're starting to cut into the principles.
That's okay.
So no, I know it's awesome, and I'm just gonna say, so why don't you take another 5-10 minutes?
So let's wrap up.
Because
Does,
then I do
does-
wanna hear
does that
from
sort of
Yes.
good?
Yeah, but
Does that make sense to, go ahead.
Well, my question is that, when the students get to algebra and calculus and all that, there's so many rules that
Yeah.
don't make sense and that you follow, right? So, I
There
don't understand
doesn't
what the
have to
difference-
be.
But you know what I'm saying?
Algebra, math does make sense, and I hope that it will make more sense when they get to upper level math. You know what, in a couple of slides I'll actually show. Don't even worry about it, because we're just going to go to the next slide anyway, Gary.
Okay, I'm gonna get rid of this.
Ryan, what happens if you get the student that was what?
I'm going to share, actually, on a multiplication thing coming up at the end, I'll share a tie-in to high school algebra.
Okay.
To try to address part of that. It doesn't have to be. You don't have to say we're going to get to a point where I no longer care if the kids understand this. I don't know why we would be teaching it to them at all if I didn't care if they understood it.
No.
Why take calculus if you don't care to understand it, right? Hopefully you're taking calculus because you might one day be interested in
Right.
pursuing a job that requires upper level math or physics
Right.
And if you are interested in that, then being able to do calculus without understanding it is not going to get you a job.
Okay.
Anyway, you have to be able to understand it to apply it in order to, I don't know, solve the problems that engineers are solving. You don't know the answer or the formula to plug in at first. If somebody knew that formula, they wouldn't have hired you as the engineer to solve that problem for them, right?
Mhm.
You were hired because you had to figure out how to bring all of this stuff together. I don't think when we went to school we were taught how to bring stuff together. We were taught how to plug into formulas.
Right.
That's why we've imported most of our engineers for the past couple of decades. We haven't been raising them ourselves here. When we talk about college and career readiness, these 8 practices are actually how college level math professors defined what it looks like to be college and career ready in math. When they had to get together after the Common Core was written and say, what is it, we keep using this term, college and career readiness, well, what exactly is that? And we had to put together a definition of that. They didn't look at the content that we're teaching in high school, the content that we're teaching in high school. They said these 8 practices, that's what it looks like. Send us kids from high school who do this.
Right.
It wasn't the content that they got hung up on, which was really interesting. Most of us really think about, oh, my child is always finishing early and she needs more of a challenge, and what you want is higher level content. And what college professors want isn't higher level content. It's more problem solving. It's more abstract reasoning. It's more making use of structure. It's more explaining and arguing and proving. That's all MP3, Mathematical Practice 3. Okay, off of that, you said 5 more minutes. We're going to go with it. So Phil Darrow is one of, I think this is like my last slide. So Phil Darrow is one of the 3 lead authors of the Common Core. He's an educator. He was the educator. The other 2 were a research physicist from Connecticut and a college mathematician from the University of Arizona. And one educator, Phil Darrow. And this is him, and he's going to talk about the difference between, at the beginning, a typical US lesson and a Japanese lesson, and he's going to introduce this term called answer getting that I used once, but I want you to think about how he's framing it.
So here's what it boils down to. A US teacher says, how can I teach my kids to get the answer to this problem? And the Japanese teacher says, how can I use this problem to teach the mathematics of this chapter or this unit? Those are really different questions. If I'm a teacher and I'm facing kids, as I will be in any real classroom, who are all over the place in terms of their readiness for today's problems, there's different ways to get the answer. One way is to teach them some math they don't already know, and then to teach them how to use that just learned math to get the answer to the problem. That's a pretty shaky way of going because my kids are all over the place. Some will learn more math very quickly. Some will struggle with it. Some, they don't have the background to learn more math. That sounds like classroom management problems. That sounds like a mess from a teaching standpoint. If I can teach them how to get the answer using math they already know, below grade level math, and maybe a few mnemonic devices, some memory aids, that's a better way to go. It's more reliable. They'll be able to get the answers right on the test. But you know what? That's not going to prepare them for the next thing they have to learn. It's not going to prepare them for next year. But that's, in fact, what American teachers usually opt for. I'm going to give you an example. Many of you have probably seen the butterfly method for adding fractions with unlike denominators. Looks like this. You draw the wings and the body, and you're going to multiply along the wings. So when you draw the body, you put an antenna on the top in the form of a plus sign as a reminder, and on the tail you put a multiplication sign. So let's multiply on the wings. 4 times 1 is 4, you write it down. 3 times 3 is 9, you write it down. Now I see the plus sign to remind me 9 plus 4 is 13. I write it in the head. Then I go down to the tail. I see the multiplication sign. 4 times 3 is 12. I write it down. Answer 13 twelfths. That's correct. It works every time. The prior knowledge of mathematics that you need to use the butterfly method is minimal. That's what it was designed for. But what the hell does this have to do with algebra? How is this preparing kids for algebra? Why is adding fractions with unlike denominators in the curriculum anyway? It's not because it's so useful. It's to prepare them for algebra. This avoids that. The butterfly method is not mathematics. When we teach kids things like this, we're adding stuff to the curriculum that isn't there in mathematics. This makes the curriculum a mile wide, inch deep. We're cluttering it with non-mathematical answer-getting methods. And this is what, this is peeling back what the word cover means. If I have to cover adding fractions with unlike denominators, and I cover it with this kind of a method, I am, in effect, avoiding the mathematics they're supposed to be learning that they need for next year's sports. And I'm building up a depth of knowledge and building up foundations for misconceptions. And what you'll see is, okay, they get these right on this year's test, but then you see this debt accumulating and they fall off the cliff, usually around 5th, 6th, 7th, 8th grade. And you'll see, oh, our elementary school is doing well, but what's wrong with our middle schools? Well, guess what? It's the elementary schools that aren't preparing them for middle school because they're teaching answer getting instead of mathematics. So we have to get rid of this stuff from the curriculum. Here's the easiest adding fractions with unlike denominator problem in TIMS. Many countries have high success rates with this. The U.S. have low success rate because of the mnemonic methods we use don't work for this kind of problem. It's actually an easy problem if you understand the principles.
Right. You can't use the butterfly method if there's more than 2 add-ins, right? It doesn't work. So this is sort of, to your point before, they get to the higher levels and they just need to do this. No, at the higher levels, we're teaching them these answer-getting tricks because we think they don't have the background to learn the new math or understand the new math. If we actually build solid foundations every step of the way so that the next grade can build on what the previous grade has built, then we don't have to fall back on mnemonics and answer-getting tricks, right? I don't want our kids to graduate thinking that math is a collection of tricks and rules to be memorized, disconnected, compartmentalized chunks of knowledge. Like there are 121 multiplication facts that are separate and distinct from the 121 division facts, right? That's kind of crazy. I want them to think math makes sense. And that's on us as teachers to teach math in a way that requires them to understand it, not just to get an answer. It kind of rocks our world because none of us were taught in that way. When teachers graded our papers, what did they do? They marked something right or wrong, and then they put a fractional grade at the top of that page. What are they saying is important? The understanding? Everything we do was built on the system of educating that wasn't about understanding, right down to how we grade the homework assignment. It's a shift. What I'm talking about is a shift. But it definitely helps the kids in the long run.